our voice is heard.
Thank you for checking. I am now recording, and could you say something?
Ah.
Yes, it is in the recording. Good. Okay, so we are
That was the first harmonic.
working.
Right?
Oh, very nice. Wow.
Thank you.
Yes,
Appreciate it.
So yes, okay. So today we're looking at Calc 2. Of course, we're doing 6.2, which is the only section for this test. 6.2 properties of power series, as it says on the bottom of the screen. Series. There you go. There's quite a bit of properties of power series, and they're all pretty important to know. I added a few things that are just useful to know. So in my notes here, again, my notes are available. Homework help, they're pinned. I added a bunch of stuff to 6.2 because as I was doing the 6.2 practice, I realized there was like a bunch of other things that weren't part of the chapter that we need to know. Not a bunch, but some notable things that weren't part of the chapter that you need to be able to do to answer the questions, like reindexing. So I added a section on reindexing in the notes, and you also need to remember from Calc 1 those formulas for finite sums, like the sum n goes from 0 to k of something, or n goes from whatever, doesn't matter. Just a finite amount. The formulas for that are very useful are necessary when you're doing the Cauchy product. So I added a bunch of those formulas there, and yeah. What'd you say?
I said clever Horowitz, trying to trick us.
Yes.
Add in stuff
from
think we know.
that we're supposed to remember from the last course. Yeah. So let me make just a general list of everything that's in this section, and we'll go from there. So first of all is like the actual, like, there's no other thing to call them except the properties of power series, so I'll just call them properties. So just properties, and there's 3 of them, right? Then we go into, I guess right after that I'll talk about reindexing. I'm gonna match my notes, the order of my notes for this one. So properties, we're gonna talk about reindexing. We're gonna talk about the Cauchy product, or Cauchy product. I don't actually know how to say it. Product. Which probably is not gonna be important because there's only 2 practice questions for it. But still, kind of. Differentiation and integration of power series. And that's pretty much it. There's one more little tiny bit that's not very important, but I'll put that in properties. So maybe there's 4 properties. I guess there's 4 properties. I'll just count that as one of them. So yeah, we're again gonna go through Horowitz's practice questions from his lectures, because I think that's a good way of doing it, and it's also very good to go over your professor's notes and the practice questions that they do, because of course it's probably what you're going to see on tests and stuff like that. So I will start with just these. No, I'm in the wrong section. There. Yeah. Okay, I'll start with the properties. What are the actual properties? And maybe I'll just list them out here. They're really just because of the fact that the sum operator, like the sum symbol, is like it's conserved over addition and scalar multiplication pretty much. So it leads to these properties here. So I should say by saying these things. So if this, then this. So it's say we have these 2 series, right? One is defined by some sequence Cn, and one's defined by some sequence Dn. Then if I try to add them together, right? Essentially, it's more useful to do it backwards. So if you think about trying to add the 2 functions together, the power series you get is with coefficients Cn plus Dn, or plus or minus, right? If you're adding or subtracting. Right, so it's kind of good to think about this one backwards. So you're thinking about the functions. Adding the functions gets you another power series that has a coefficient Cn plus Dn for all n that we're talking about.
Wait, I have a question.
Yeah.
So for these 2 power series, everything else is the same. Like where it's centered, everything is the same.
Yeah, they're centered at the same. They're centered at the same spot.
And then the I is the same, and the only difference is the coefficients.
I doesn't actually have to be the same. I doesn't actually have to be the answer. So I didn't really write that here, and I guess I should add that to my notes. So this I is the minimum of these 2. So let's say
Yeah,
this
like-
one was -3 to 3, and this I is -2 to 2. This I will be -2 to 2.
So it's like where they intersect.
Where they intersect, exactly. Where the two sets intersect. That's right. Right?
Okay, so and then everything else is the same. It's just like the coefficients.
Everything
and
else
the
is the same, yeah. The coefficients is what makes them different power series, right?
Mhm.
And then, so when you try to add them together, their sum is the sum of the power series, of the sequences, I mean.
And same with like minus. So like if you subtract
Yeah,
them, it's just...
that's why it's plus minus here.
All right, thank you.
No problem.
So the x minus a to the n is going to be the same for both of them as well?
Yeah, x minus a to the n has to, I'm quite certain they have to be centered at the same spot. I don't remember them ever being... Yeah, that doesn't make sense for them to not be centered at the same spot.
Mm-hmm. Mm-hmm. Okay.
So the next property is this one. So essentially, this is just saying that scalar multiples of a real scalar, like I mean that exactly, real scalar, like a real number and a scalar, that's a scalar, and that multiples of x, or powers of x, they're all, they can all be taken out of the sum, right? Because then if I take this out of the sum, it'll be bx to the m, take that out, and then you literally just have bx to the m f of x, and which is what it's saying. It does actually converge to bx to the n, or, oops, I realized that should be an m. That should be an m there. That's a typo. It should be an m right there. Yeah, I have to write that down to fix it. Well, okay, hopefully I'll remember. I won't remember, but let's see. So all this is saying is that, yeah, it's just that you can actually take out literal real scalars and also multiples of x out of the sum, and the remaining thing, after you take those things out, will converge. If it looks like Cn, x minus a to the n, it will converge to f of x. Right? So b and x, b and m can be any real numbers here. Yeah. So, and m is some sort of positive integer. This means positive integer. And b is a real number. Okay, and then this one is essentially saying that if you can have the function, the power function, evaluated at some value. So if you evaluate the power function instead of just at x, you can evaluate it at x to the m or bx to the m. Well, what effect does that have? It has this effect. So a lot of these rules are actually, like the first and the third rule are good to actually think about backwards. Like what if I wanted to evaluate the function, which is defined by the power function, at something that's not x, that's maybe like 2x squared, then this is how you do it. Right, the b goes there, the m goes there. And yeah, that's that. Okay, so we're going to use these rules. We're going to use them to solve some sort of problems. But how do people feel just hearing the rules so far? Let's see.
I don't know, that last one's kind of confusing to me for some reason.
Okay, we'll probably get to a practice question for it. Maybe it'll make more sense after we get to
So
the
the
practice.
last one simplifies to f of that b x n m.
Yeah, if I have some function, right? If I have this, if this is how I define f of x, right? This is how I define f of x. Then what's what's f of bx to the m? This is f of bx to the m. So it's probably good to write bx to the m is this sum. This sum n goes from 0 to infinity. Okay, so Cn stays where it is. Then what's in the to the n term? So, or to the n part of the product. Well, what's there is it's gonna be effectively bx to the m, but since we're centered somewhere, it's x minus a to the m.
Unless it's a 0.
You just have to, well, yeah, except unless a is 0. But if a is not 0, then you're centered at some a, right? And you'd write it like that.
All right, thank you.
Which is essentially just plugging something into a function. It's just that you have to remember that a power function has an extra property that you don't put in, and that's like what it's centered at. And so you have to remember to include that here. That's like your x value, right? But other than that, it's just plugging in something into a function. So let's try this one. So I guess I'll just go for it. So the first example from Horowitz's lectures is, suppose we have two power series. The sum, so I'm gonna just write an n on the bottom. If I just write an n, that means from n equals 0. I just want to cut down on my meaningless writing a little bit. So we have the sum from over the n's, n goes to 0 to infinity, from 0 to infinity of a n x to the n, and it converges on x is between -3 and 3. Okay, x is in -3 to 3. And then we have another series, which is the sum over the ends of bn x to the n, which converges on x is between -2 and 2. So given the fact we have these two, we don't have to worry about what the functions are or what they converge to. It doesn't matter. Given the fact that we have these two power series, we have to say write an expression for the sum. Hold on, did I write that backwards on the thing? I think I wrote that backwards on the thing. Let's just skip to the next one. So there's like a few parts to this question, so I'm going to skip the first one. Write an expression for an 2 to the n x to the n. Right? So over the n's to infinity. And what is the interval of convergence? Find I for. So the question is find the interval of convergence. Write an expression. Find the interval of convergence for this. What's the interval of convergence for this one? Well, it's not too hard to figure out. We know that an x to the n converges on -3 to 3, right? So then what does the sum over the ends of an 2x to the n converge on? Right? Well, here x has to be between -3 and 3. Well, now 2x has to be between -3 and 3. Right? And I just want to get the writing clear. This is completely identical to -3 less than 2x less than 3. It's just sometimes easier to write it like this. But I'll carry on like this for now. So -3 over 2 is less than x, which is less than 3 over 2. So the interval of convergence is, I is -3/2 to 3/2. Do we have to check the endpoints? He didn't check the endpoints here. So I think we don't have to because this is defined as converging, not inclusive of the outer bounds here. And there's no reason. So essentially here, right? Essentially here we used this third rule. We used the third rule here, which is an important thing to note here, is that if you evaluate the function at something that's not x, you have to make that thing that you're evaluating it at as part of I, right? So that's what I did here. This step right there, bx to the m in I, that is what I wrote right here, which is bx to the m, right? Because b is 2 and m is 1. So it's 2x is in I. And this is our original I, -3 to 3. So now our interval of convergence is this. Remember, the question is just find the interval of convergence. Okay, so that's the interval of convergence for this one. And then for part B, it's find the interval of convergence, the sum over the ends of, so an plus bn, x to the n. So the interval of convergence for this, to figure that out, well, the interval of convergence, an equivalent power series is an x to the n plus the sum over the ends of bn x to the n. And, well, what's the power series? The interval here is negative, what was it? -3 to 3. Yeah, -3 to 3, not inclusive. And the interval here was -2 to 2, not inclusive. So we take this one. This is the interval of convergence for this whole thing. So the interval of convergence for the whole thing is -2 to 2. Because they both converge, both of these things separately converge to their functions, whatever function, between -2 and 2, but not between -3 and 3. Only one of them goes between -3 and 3. Well, -3 to -2 and 2 to 3. So we gotta choose the bigger of the two, because we're separating this into that. That's using property number 2, and this is using property number 3. Right? So using property number 3. Actually, effectively. Oops. This is pretty much using property number 3. And yeah, so those are the intervals of convergence.
Yeah. Adam.
Yes.
You said something about having 4 properties. You did.
Oh, you're
mention
right.
Bosco.
Yeah. So because it's at the end of my notes. So yeah, you know what? I will
Okay.
mention it now. It does make sense to have
Okay.
to put it here though. It doesn't really make sense at the end. It's called the uniqueness of power series. So all that means is that if you have 2 power series, I'll just put it here. And this is the uniqueness of power series. So if you have a power series Cn, you know, the coefficients are defined by some sequence Cn. Another power series where the sequence is defined by Dn. They both converge to f of x on the same interval, then Cn must be Dn. There's no other. So if you have like one interval and you have 2 different power series that both converge to f of x on that interval, then they must be the same power series. That's essentially what that means. They could be centered at different bits. They could be centered at different places, but like at different parts on the interval. But if they are, I mean, here we have it x minus a. Then if they have the same sequence that is defining the coefficients, they're the same sequence. That's all that means. Not like that useful. It's kind of maybe will pop up as something to mention in some questions, but I don't think there was even like a practice question about this. So because there's not much to practice, it's just a theorem about this stuff. So yeah.
Could you just go up to the very first two? Was it an? Like they already gave us the convergence, which is negative 3 to 3.
Yeah, this is
Then
what's
we had some-
this is what's given. This is given.
Okay, and we see. Wait, so bn is just the 2x to the n part.
Um,
Kind of got mixed up right there.
Bn is just an entirely different. Power series here, right? This
Okay.
this first section we're just talking about the first power series, which is defined by an, right? And we can rewrite this as this, and then we essentially
Okay.
use property number 3 to find the interval, because if we're evaluating f at something that's not at just x, then
Yeah.
the interval is that thing in the interval.
So considering that we already were given the interval for an, we're just finding this kind of coefficient.
Yeah, exactly. We just had to put this element of the convergence for an, which was negative 3 to 3,
Then solve for it. Okay.
and solve for
Okay.
what x has to be in that interval.
So why did you say? Did you say that the bn now was negative 2 to 2?
Yeah, that's for the next part here. Bn is negative 2 to 2. Right, so this new power series, which is the sum of them, is, by property 2, the same thing as this, each thing individually.
Yeah.
So this converges on negative 3 to 3. This power series converges on negative 3 to 3. This power series converges on negative 2 to 2.
Wait, was that given?
That's given. Yep,
Oh, okay.
that's part of the question. So based on that, this sum converges on the smallest interval that's shared between
Yeah.
them, right?
Yeah. Okay. That makes sense.
Or just the interval that's shared between them.
Yeah. So as you said, like as long as it's for the first part A, as long as there's something apart from just x, we have to set that to the
Yeah,
interval.
you have to
Yeah,
to find the interval of convergence. It's essentially just the
Yeah.
like it's sort of what we would already do.
Mhm.
It's just more in general now. Like this is just like
Okay.
in general.
All right, thanks.
No problem. Okay, I'm gonna move on. But if anybody has any questions, just let me know. The next one is to represent these rational functions as power series. So 2x squared over 1 plus x cubed. This is still going to use the properties up here. It's just to do another question. So express this rational function as a power series. Right? So how would we do it? Well, the only power series I essentially know how to write, or the only function I know how to write as a power series, is 1 over 1 minus a, or 1 minus r, or a over 1 minus r, right? So we're going to treat it as 1 over, because this isn't, even though this is technically a constant because it's for some fixed value of x, it's okay to think about this as a. Usually how they do it and how it's done in the text here always is that you write this as 2x squared times 1 over 1 plus x cubed. Because it's a little bit more clear that this is the power series, or it's only one step away from being a power series. Because I can rewrite this as 2x squared, times 1 over 1 minus x cubed. And now this is directly just this is directly just 2x squared times the sum over the ends of, well, a is 1, so negative x cubed to the n, to the n. And that's a power series now. Now I can simplify this a little bit. It's not like just a nice single power series. Using property 3, I can move this constant multiple in. So it's going to be, property 2. Property 2. I can move this constant multiple and this x to the n, or x to the 2, not x to the n, in. So it'll be 2x squared times negative 1 to the n, x to the 3n. Sum over the ends. And this can simplify more into sum over the ends of negative 1 to the n, 2x to the 3n plus 2. And now we just have to find the interval of convergence, which we do from here, right? So actually it doesn't ask for the interval of convergence, but we do need to find it also. It's also good to know. So I is,
Does it change anything that it's alternating?
No, because to do this step, this is where your convergence this is where your condition on the convergence comes. This step right here, right? So that's
Okay.
yeah. It just
So
means
it
that
wouldn't change anything?
it wouldn't change anything, no.
Oh.
Negative x cubed is an element from negative 1 to 1. Right? The reason... Yeah, sorry.
What do you mean about to do that previous step? You just need the negative x cubed. What step are you referring to?
And also, for the person who asked if it changes anything, if it's alternating, just remember to take the absolute value of r when you solve the question. So it doesn't matter if it's alternating or not.
We check that r is between negative, the absolute value of r is between less than 1. So that's what, it doesn't matter like that. It's good to just think about, like, to do that step that we just did right there before the green arrow. I'll draw it. To do this step, the condition that is created is that r is less than 1. And that's the condition I have to check here. R is negative x cubed, and it has to be between negative 1 and 1. Should say absolute value, sorry. A little bit. Yeah. So does that make sense? So now I just have to check this condition. So it's just going to be x cubed is between still negative 1 and 1. X is between negative 1 and 1. Still that, yeah. That didn't change anything. So it still just converges for negative 1 to 1. So does that make sense?
You do not include the 2?
In my interval,
Yeah.
I don't include it because that's not part of what the condition is. The condition is on R here, right? R is part of the condition. That's what decides when things converge or not. So R in this specific case is negative x cubed, so I only take into account negative x cubed.
Oh, okay.
Right?
Wait, so to get the r, we ignore the b, like everything else, just take
Yeah.
the pure form?
Yeah. We just take the thing that's R in this case, because 1 over 1 minus R, right?
But like, how about the x thing, like outside? Once that comes in, doesn't that affect r?
It changes the value of R, but at this point we've already determined what the condition is of convergence. This is the condition of convergence, right? So we know that this is what x has to be. For this to converge, you can think of it like this. This is just a constant multiple, right? It does contain x, but it's just a constant for some fixed value of x, right? This is a power series, right? this is a power series. The power series converges if r is less than 1, and then you just happen to be multiplying it by a constant. But that doesn't change. The power series converges if r is less than 1.
So whenever you do one of these questions, just treat that thing like it'll be a 5 or a 6. I don't ignore the x
Yeah,
part.
it's just, I mean, you're going to use the x part. You have to take, because I put a +2 here, right? You're going to use the fact that it's an x.
When doing the interval, you kind of ignore that. You just
Yeah, when you're doing the interval, you just take into account r. Yeah, that's all you need.
I thank you.
No problem. Okay. So, any more questions about that one? Or same question, but different function now. 1 over x plus 2, x plus 1. Oh, sorry, it's x minus 2. X plus 1. Yeah. So to do this one, well, we just do partial fractions, right? We just do partial fractions. And I'm just going to save us a little time here and just find what the partial fractions are. So the partial fractions are 1 over 3x minus 2 minus 1 over 3x plus 1. Okay, so that's the partial fractions. Now, write that a little nicer. Now, each of these things independently can be turned into a power series, right? We can take the 1/3 to the side, right? And this is going to be x minus 2. But if I make that, multiply this by -1, it's going to be 2 minus x. And I can move the -1 to the top, or I can just move it out to the front here. Okay, so now that's a power series. 1 over, so minus 1/3, 1 over x plus 1. Now I have to turn x plus 1 into 1 minus something. 1 minus something happening to x, right? So it's probably good to turn this into 1 plus x. Now, I want this to be a minus sign. So if I make that a minus sign right now, it's not, so before we had 1 over 1 plus x. I have to remember, this has to be equal to 1 over 1 plus x. So if I just make that 1 minus minus x, then that is the same thing now. That is equivalent. Right? So we're good. Both of these things can be turned into power series just with a constant multiple of 1/3. So -1/3, the sum, n goes from 0 to infinity of, oh, sorry, not quite done with this one here. This is not 1 minus yet. This is 2 minus, so we don't want 2 minus, but we want, it's going to be -1 over 6, 1 over 1 minus x over 2. Now, -1/3, 1 over 1 minus -x. Now this can be turned into a power series. 1 over 6 times the sum, n goes from 0 to infinity, of x over 2 to the n, minus 1/3 the sum, n to infinity, of -x to the n. And take a sip of my water. And we have now that this is, what are we looking for? Single power series, right? This is a single power series. Well, we know, let me first simplify a little bit. The sum n to infinity of, so this is going to be x to the 1 over 2 to the n, x to the n, minus 1/3, sum -1 to the n, x to the n. So now, essentially, we're going to use property 1. Well, I guess I'll factor out the... no, to use property 1, actually, I have to put in the constants into it. So first I'm going to write that. So it's going to be the sum over the n's of... So this is going to be 1 over 6 times 2 to the n, negative 6 to the n, x to the n. And it's going to be plus the sum n to infinity of... Now I'm moving a -1 in. So this is going to be a -1 to the n plus 1 over 3 x to the n. Now I can use property 1, which is saying that if I'm summing two power series centered at the same number, then the effect of that, and they both converge, then the effect of that, they do both converge because we showed it here, right? Then they will converge to this, which is negative 1 over 6 times 2 to the n. They're adding together, so plus negative 1 to the n plus 1 over 3 x to the n. And is that the answer? Negative 1 over 6 times 2 to the n plus negative 1 to the... it doesn't really matter, yeah. Plus negative 1 to the n plus 1 over 3. Yeah, that's the answer. And now interval of convergence is also something to ask, but we'll do that in a second.
Yeah, what's this one question? Can you just like read it again? I guess your speed run.
Like explain the question again?
Yeah. Did you do partial fractions and then?
I did partial fractions here, yeah. Let me just find the interval of convergence and then I'll explain the question. Partial fractions. Right, to go from there to there. So now, interval of convergence, well, where did the restriction come from? It comes from here. X over 2 has to be between negative 1 and 1. Then, so I'll find the restriction on that. Well, X has to be between negative 2 and 2, right? Then, over here, we get that negative X has to be between negative 1 and 1. So X has to be between negative 1 and 1. So just to be clear here, these are two separate conditions we're checking. This is the condition from here, and this is the I'll do a different color. This is the condition from here. And so what's the smallest? Well, this is the smallest, right? So that's the convergence of the final answer. The interval of convergence of the final answer is not including negative 1 to 1. Okay. How does that sound? Does this make sense?
Yeah, no, can you like just go through?
Sure. So this is with the fraction that we're trying to write as a power series, right? Partial fractions separates that into two separate fractions. A little bit of manipulation to get them in both into the form a times 1 over 1 minus r, right? Because this we know how to write as a power series. So I manipulate both of them to look like a times 1 over 1 minus r, a times 1 over 1 minus r. Now that they both look like that, I can right away turn them both into power series. It's going to be x over 2 to the n, negative x to the n. Okay, I simplify a little bit. I distribute the power of n in. So they both have an an and a bn, right? They both like have their own sequence that's defining their terms. And then I move the constants in so that I can use property 1. This is property 1 that I use here. This is property 1. Property 1, which is this. And that's my final power series. It's not very, maybe I can simplify it more, but it doesn't really matter. It's a single power series. And the interval of convergence comes from up here. So the interval of convergence comes from this step. This is the power series step, which gets us two different intervals of convergence, negative 2 to 2 and negative 1 to 1, based on the two different power series, which we're getting here. The smallest of the two, right, the smallest shared interval will be the interval of convergence for the whole thing. Right?
What rule was this one using? Sorry, go ahead.
I was gonna say, do we need to check the endpoints for this, or do we just assume that the endpoints are always going to be?
You don't need to check the endpoints when you do this step. When you do a geometric series to the actual series, right? Like the.
Okay. Yeah, that's all. Because usually, like before, when we were asked for interval of convergence,
Yeah.
you wanted it. They also wanted you to check endpoints, but I guess for this it won't.
You know it won't, because the condition here is that the absolute value of r is less than 1, not less than or equal to 1,
Okay.
less than 1, right?
Alright.
So the endpoints would be where it is 1, right?
Wait, I just joined. Can you tell me what I missed?
We did.
Yo, everything we solved,
we-
whole...
We talked about the properties. We solved 2 questions, 3 questions. This is our 4th question.
You can watch the video if you want to.
The video this is recorded, so you can watch the video after.
Yo, Adam, on that last bit, can you just go on the second to last line? So like you just put them in. You brought the coefficients back into the power series, and that was about it. Then you just since it's addition, that was rule what, 3 or rule 4?
Rule 1. That's rule 1 here. This
Really?
one here, right? So if you have two separate series and you add them, then you converge. It gets to Cn plus Dn.
Wait, I'm mixing it up with the other one where it's like if Cn and Tn equal to so. But yeah, that makes sense.
Yeah. They're different here, but you're adding them together, so you use that rule.
So it says if you add them together, what if they're centered differently with the x minus a?
Then I think they don't add like that. I think.
So how do we even determine the? So I'm just thinking.
How do you determine what?
So you said, like if you look back at it, it says like if x minus a, right?
Yeah.
So that would mean that they're like centered differently, but like we haven't really stumbled or anything like that.
They're both centered at the same spot. So these two that we got in this question here, these two power series, they're both centered at 0.
Oh, which is okay.
Because there's no a, it's just x. It's just x. You can say x plus 0, right? And then a is 0.
Oh yeah. But that one had x divided by 2. But
yeah.
It's not like that.
But if it was centered, it would be like x minus a over 2.
Oh, okay.
If it was centered at something else, right? But this is just x over 2.
There has to be a number like added or subtracted like right
from the x. Yeah.
From the x. Alright, so unless it's that, we can just move on with this. Alright, thanks.
Notably, it has to be adding or subtracting from the x also to the power of n. Right? It has to be in the exponent of n. So like x plus 2, all that to the power of n or whatever. Okay. So the next one is find the function represented by the following power series and its interval of convergence. So find the function that is, so this series, sum over the n's of 3 to the n x to the n equals f of x. Okay, well, find what f of x is and what's its interval of convergence. Well, we know that this left side can turn into the sum over the n's of 3x to the n, which is f of x, and f of x. Then this is the sum over the n's. Well, sorry, this can just turn right away here into 1 over 1 minus 3x equals f of x. And we're done.
I have a question.
Interval, yeah.
What do you put for the index for n? Do you just leave it as n, or do you make it like n equals 0?
Yeah, I'm just writing n, but when I write n, I mean n equals 0 here.
Okay, perfect.
Right?
Okay,
Yeah.
Thank you.
Yeah. Just to save a little bit of writing. Just write n, yeah. So 3x has to be between -1 and 1, which means x has to be between -1/3 and 1/3. Right? And there's that. So that's our function. That's our interval of convergence. Okay. So let's see this quickly. Yeah. Okay, that's everything for the practice I have of just using the properties.
Yeah, what was that one just now? Was that just like the first question that you gave us?
This one
Like,
here?
Yeah, it was similar to the very first one where you just like found.
Yeah, I guess it is kind of similar to the.
Sorry, could you just go over it?
This one here. It is kind of similar to this one. This here, well, this I'm just trying to write it in the form of something to the n, because I know if it's in the form of something to the n, then I can write that as 1 over 1 minus the something. Right. That's the geometric series rule, right? So I can just do that in one step here because it's 3 to the n, x to the n, so it's 3x to the n. 1 over 1 minus 3x is f of x. And then using the third rule, what's the interval of convergence? Well, the interval of convergence is going to be 3x is between -1 and 1. not even actually using the third rule. You're just using the geometric series rule, like just the convergence of geometric series.
Okay.
Of
Wait, this is just using. Well, you said geometric series was basically the power series rule, where it's like from 1 over 1 minus r. It's from -1 to 1, and then you just solve for the 3x, right?
yeah, you figure out what x has to be,
Okay.
not 3x. Yeah, you have to figure out that.
Yeah, sorry, x.
So yeah. Okay. So, how does everybody feel about the property stuff?
Pretty good. Is this textbook questions?
This is from Horowitz's lectures, but I am actually going to do some textbook questions for the next bit. I'm actually going to skip to some textbook questions, and we can do textbook questions at the end. Okay, give me 1 second, guys. Give me 1 second.
These are from the man himself, Horowitz, from the source.
You do be your plug, yeah.
Hell yeah. Hell yeah.
Yeah, Adam just gives us right from the source, right from the, it's right from the source.
Yeah, I'm not like that, guys. Don't get too surprised, but legend has it that some of us don't attend classes anymore. We just wait on Adam. Legend has it. I won't say.
I don't know if that. I mean, would that work? Could you do that? That's
Of
actually.
course it does. Just use the
Are you challenging me? Man's like, do it, you won't.
Nah.
Next semester.
Yo, what are we gonna do with Adam, bro? He's gonna be in a whole different. Oh my gosh.
What do you mean? Why?
Because we're gonna be doing completely different courses as time goes on.
Yeah, that's true.
We'll have
Oh.
Eventually we'll get different courses, but we'll all have
Exactly.
math. And come on, it's.
And his favorite course is math, so.
It still hurts to think about it.
It is, right, Adam? Favorite course is math?
Oh yeah, I'm liking math. That's for sure. I'm
I like
liking.
math. I'd say physics.
I feel like Adam is one of those guys that just does math for fun. Like he's just like, yeah, it's nothing to do in quarantine. Just do some math.
That's true.
Wait, actually?
Yeah.
Actually,
Well, yeah, I like math. I do math.
like, do you do it for
All of
fun?
us like math. We just
Yes.
don't always do well in it, right, guys?
Yeah.
Come on, give yourself some.
Yeah.
If your YouTube feed ain't filled with Veritaserum and
Yeah,
number file,
number file. Yeah, that's
Yeah,
true.
yeah.
You're not a real engineer.
Call us alright, dude.
I like 3 brown, 1 blue. That guy is so good.
That guy's so good.
course.
It's
No,
the
like,
rites of passage, man.
Guys, we're gonna spend another 10 minutes
Yes.
talking about
Let's
nothing
get back.
until
Let's
we're
get back to. Let's get back to it. Thank you.
I like you donut.
Okay.
Can I get a coffee? Do you drink coffee?
I don't drink coffee very much.
Do you like donuts?
Sure.
Cauchy Product, come on.
Yeah.
We're going on a tangent again.
Okay,
alright.
let's go. That's enough. Yeah. Okay.
We
Let's
got
go.
this, let's get this,
So-
let's get this.
The Cauchy product is something that's part of 6.2. It's essentially how you multiply two power series together. So if I have two power series, both centered at the same spot, they can be both centered at A. It doesn't have to be 0, but just for the sake of the definition, you just write it as centered at 0. But they're centered at the same place, and their index both starts at 0. Then if you try to multiply them, you get this expression. This is what the product is defined as. And so it's a lot to unpack here. The best way to think about it is that, which I literally write here, the best way to think about it is that this inner sum, you usually just call that En, which is just part of the product. That inner sum is, if you notice here, so you see it's a sum within a sum. That's a finite sum. That's a finite sum, which means it's not an infinite sum, right? This doesn't go to infinity. This goes to a finite number. And so it always, not always, but for all the questions that we'll ever have for it, it will simplify to something. It will simplify to actually an expression. So let me just explain what's happening here a little bit. If I have two power series, right? If I have f of x is the sum n goes from 0, cn x to the n, and then I have g of x, which is the sum over the n's to infinity of dn x to the n, and I want to multiply them, right? So f times g of x, f times g of x, f times g of x, right? What is this? Okay, let's write out the first few terms of what's happening here. right? Let's write out the first few terms. So the first few terms of this power series up here is, okay, so it's going to be C0 plus C1x plus C2x squared plus C3x cubed, dot, dot, dot. And I'm trying to multiply that with D0 plus D1x plus D2x squared plus D3x cubed, dot, 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 like that, right? So if this was a polynomial and I ended it here, this is just a polynomial, then you'd be able to multiply that, right? You just multiply each term individually, and it'd be a process, but you'd be able to do it, right? But it's an infinite sum, so we have to try to figure out a pattern that's happening here. So the product is also going to be a power series, right? It's also going to be a power series that has some sort of sequence defining it, right? So let's take a look at the constant terms. If I wanted to get a constant term out of this product, there's only one way to get a constant term, and that's when I multiply C0 and D0. I multiply any two pairs other than that, I'm going to have an X in there, right? So I know my constant term, at least, for the product. The constant term is C0, D0. Okay? Now, what about my X term, just with an X in it? How do I get just an X? Well, I can either multiply... Yeah? Someone's going to say something?
I was going to say it's D1x times C0.
Yeah, D1x times C0 or C1x times D0. Or, yeah, or these two. There's two options for how I could get it, right? So either C0 D1 or C1 D0. Okay, now let's take a look. How could we get the X squared term? How could we get the X squared term? Well, there's a few more ways, and it's going to get more and more complicated as we go up in term numbers. And so, well, how can I get it? Okay, first of all, I can get C0, I'll do it a different color, C0 D2x squared. I can multiply those two. So C0 D2. Right, I'm just factoring out the x squared, so it's just to the side there. Hopefully that makes sense. I could also do C1x D1x, right? So plus C1 D1. Or I could do C2x squared D0 plus C2 D0. And those are the only three ways I can get an x squared term, right? And it's going to get more and more complicated as I go on, right? So let me do the x cubed terms as well. And that'll be the last one I'll do. So dot dot dot. How can I get x cubed? Well, I can do C0 D3. C0 D3. I can do C1 D2. C1x times D2x squared. So C1 D2. I can do C2 D1. C2 D1, or finally I could do C3 D0. C3 D0. Okay, so let's see if we can see a pattern here. What'd you say?
Is this supposed to be an addition sign right here, or no? With C
Yeah,
0.
right there?
Yeah.
Yeah, there's supposed to be addition
I
sign.
thought this was multiplication or something. I think.
Pattern.
So there's the pattern. Yeah, what pattern do you see?
Isn't it like C just like the thing that subscript just keeps increasing, and like for C, and like it just keeps decreasing for D?
Yeah. Well, like so let's try to think about it like this. The x to the n term has some coefficient, right? Has some coefficient here. What is that coefficient? Well, it's what I want you to notice here is that the index variables, so this is the x to the 0 term, we can call it the 0 term, right? The indexes add up to 0. This is the 1 term, x to the 1 term. The indexes add up to 1. And this is the 2 term. All the indexes in each term add up to 2. 0 plus 2 is 2. 1 plus 1 is 2. 2 plus 0 is 2. And if we look at the third term, right, the third section, the third coefficient, right? The index variables all add up to 3 in each term. So 0 plus 3 is 3. 1 plus 2 is 3. 2 plus 1 is 3. 3 plus 0 is 3. So in general, we're going to have the sum. It's going to be a sum. How many items are going to be in it? Come on. It's going to be the sum. N goes from 0 to, or it's usually written as k goes from 0 to n. Yeah, so k goes from 0 to n of, right? So if this was the the 0th one, n equals 0. So what's the coefficient on the x to the n? Well, x to the 0, it would be c of that number, right? C of that number, cn, d to the k dk minus n. And so try it out a little bit here, right? If I say we're talking about the third term, right? Let's do an actual example here. We're talking about the n equals 3. So what's the coefficient on the third term? Or let's try to figure out, well, let's do a third and then maybe we'll do fourth after 2. What's the coefficient on the third term? Well, it's going to be the sum, k goes from 0 to 3, of cn dk minus n. Right? So that's going to be, well, c, yeah, the n is, so this should be 3. Oh, sorry, did I write it wrong? Hold on. It shouldn't be dk minus, it should be n minus k, not k minus n. N minus k here, sorry. It's n minus k. Right? So this sum, just I want you to notice here something. This sum right here, n plus n minus k, oh, that will be not what I was expecting. The k's go from, yeah, sorry, I should have looked at my notes when I was writing it. ck, the index variable is what's increasing. That's why I was getting confused. The index variable is what's increasing. So the first one should have a k on it, and then n minus k. Because if you add that together, right, k plus n minus k, we get n. That's the whole property. That's the important property that we have here, is that the index variables of the two parts of the sequence add up to just n, right? So for example, here in the third term, right, it's going to be k 3 minus k. And the index for any value of k is going to be k plus 3 minus k is going to be 3 for any set value of k. So to find what the actual coefficient is on the x cubed term, well, okay, start at 0, k equals 0. So c0, d3 minus 0, d3. Plus, now k is 1, c1, d2. Plus c2, d1, plus c3, d0. And it's exactly what we got up here. So in general, what that means is that the nth, the coefficient on x to the n of the product is going to be this. Is going to be this sum. So in general, the sum, so if I have f of x times g of x, that's going to be equal to the sum of, from n goes from 0 to infinity, of this sum, right? This sum, k goes from 0 to n, of ck d n minus k x to the n. This is just a coefficient. This is just a coefficient. Right? That's just a coefficient. And we're adding up all the x to the n's, right? X to the 0, x to the 1, x to the 2, with their specified coefficient. Right? And how do you figure out what that coefficient is? That's how you figure out what the coefficient is. The reason that we can actually make any sense of this is because this coefficient always simplifies. Simplifies for any question we'll get. Right? It'll always simplify to something simple, to something nice, to like an actual expression. And so then you can just use that as your coefficient. That'll just be your coefficient.
Okay, Adam.
Yes.
For that, so I'm having some trouble thinking about this because you say it's a coefficient, but if you just go to the bottom, yeah, this one. So it says that it goes from k equals 0 to n, but on the outside, n is going to infinity. So how's that finite?
The polynomial is infinite, but the actual coefficient is a finite number. Right? The polynomial itself, like look here, if I write out the first few terms, right?
Yeah.
So I already have it written here. If I write out the first few terms in general of this polynomial, it's an infinite polynomial. You see the dot 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 at the end, right?
Yeah.
But each coefficient is a finite sum,
Okay.
right?
Oh.
Each coefficient
oh,
is
I
a
see.
finite sum,
I see.
right? That's just some number. And to figure out what that sum is, you do this.
Oh well, is you could also say that the number of terms in that coefficient is 1 plus the index, 1 plus n.
Yeah, 1 plus, that's the number of terms. Yeah, that's kind of more because of how the sequences work, or how the sum operator works, right? You count 0. You start counting at 0, right? So 0 is the first one, right?
Okay.
Yeah.
Okay, makes sense.
Right.
Thank you.
Yeah, no problem. So, okay, how do we simplify that coefficient? Well, we simplify it by using one of these properties, which is sum from MTH 140 and some extra ones that I added here. They're all available in my notes. So helpful finite sum formulas.
Do they even give these to you, or are you supposed to like solve them without like?
You're supposed to know them, I think.
Okay.
This one, these are from 140, MTH 140. These are from MTH 140. The rest of them, this one's useful. This one I had to use this one for one of the practice homeworks, which is why I decided to add all of them. But yeah, so I had to use this for one of the textbook questions. And these other three are I just threw in there because it could be useful. I don't know. So yeah, so let's do a problem. And actually the best example I have is a textbook question, which is good. Let's do an example of actually solving one of these problems, and you'll see what it's like. I actually only really have one example, because the other example I don't know how to do, and the only one example that Horowitz did, it's one that's like complicated in a way that wouldn't appear on a test, if you know what I mean when I say that. Like it's not like a test-worthy question. It's just complicated because it's kind of confusing how you have to deal with it.
Classic Horowitz.
Yeah, there are a few examples that are.
You know, I think those questions are the ones that are going to come on the final.
Well, I know what you mean, but I really know this one isn't. I really know this one isn't going to be. It's like it's just sort of.
What you didn't know how to do, but was like before you said the Horowitz one, because you should do that one.
We can do it after. This one I know how to do, so let's do this one first, and then the one after we'll try it. Yeah. So this one, the question is find f times find f of x times g of x, right? Find the product using the Cauchy product. Okay. So, well, I need to explicitly write out what's happening here. So f of x is the sum, starting at 0, of 2x to the n. I move the 2 in so that we can see exactly it's in the form an x to the n, right? And g of x is the sum, and goes from 0 n x to the n. So I want the product of these two, right? F of x times g of x is going to be, by definition, the sum over the n's to infinity of en. I'll just write it like this, of en, x to the n. Now I have to figure out what en is. En is this thing right here. This inner, nope, that's not en. Why did I write en there? That's en. That's en, right? It's this inner en is the coefficient, right? That's that inner sum there. So now I have to find an expression for en. En is the sum, k goes from 0 to n, of c, k, d, n minus k. Okay, what's cn and dn? So here, cn is 2, dn is n. Now I'm going to do a trick here, and I'm just going to switch them up, and I'm going to call cn n and dn 2. The reason I do that is because this is a more complicated sequence value to find, dn minus k. And so if I can just make that the constant 2, that'll simplify things a lot. And I'm allowed to do that because product is, I forget the word, but you can flip the product both ways, right? So f
Commutative?
is that, if that's the word, commutative. Then there you go. Yeah.
It's either that or associative.
I think associative is with the brackets.
No, it's commutative.
Yeah, commutative I think is.
Okay,
So.
commutative.
So then this is just going to be n times 2.
Where did the e of n come from? From your
Yeah, I was
f
going to ask that.
plus g of x, f of x times g of x.
En is this inner coefficient here, this inner sum. That's just by definition. I just say En is the sum. K goes from 0 to n of ck dn minus k.
Oh, okay, I got it.
You do that just to simplify it a little bit, just to separate it. Think about something else for a
You
second.
don't need to work on that right now.
Right? Yeah, exactly. You just what we need to find is that expression for the coefficients. Right? I know each term is going to have an x to the n, but what's the coefficient in front of that? Okay. So here I have En. This is going to simplify because En is going to be, now I can move the 2 out. 2 times the sum k equals 0 to n of n. Right? So I can do this. Oh, sorry, it should be k. It should be k. It's ck. The variable's k, right? The variable, it's ck there, so there should be a k. So k goes from 0 to n of k. Yeah, that's what it is. That can simplify using one of the rules from up there. That's 2 times, well, what's the sum? This right here. n plus 1 over 2. Which is just n plus 1. Okay, so we know that the, x to the n term will have a coefficient of n plus 1. So I can finally write the product, f of x times g of x, as the sum over the n's of en x to the n. But en now is just n plus 1. And that's the product. And that will not only is that the product, that will converge to f of x times g of x. Right? That will converge to f of x times g of x.
Can you go to the around the middle of this?
Yeah.
Right there.
Here?
Mm-hmm.
What
do they mean by c sub k?
C sub k?
Mm-hmm.
It just means you take the Cn, like you can define C in terms of n, and just evaluate it at k. Right? K is just the index variable, so it's just a different variable that we're evaluating it, right?
Okay. So then you just turn that n into a k, and then we just saw.
Exactly. So it's Cn is n, so now I just put a k there. Right?
I have a question.
Yeah.
I forgot. What do you mean by it converges to f of x times g of x? Like you multiply like their interval of convergences? Is that what you mean?
Interval of yeah, I should figure out what their interval of convergence is. I don't actually know. Let's see. What I mean by that is that, like, if our original function here, what did I get? If this converges to some function f of x, right? This power series here, and this function converges to some function, this power series converges to some function g of x.
Mm-hmm.
When I multiply them using the Cauchy product, that product will converge to f of x times g of x. As in, on some interval, if I plug in some value in for f of x times g of x, right? I'll get that same value here.
I thought it literally meant like, the interval will be like the product of the intervals.
No. This just means like the actual values, the functions evaluated at these values are the same.
So how did you go from 2x to the n and x to the n, or whatever it was, to e to the n? I got kind of confused right there.
Here?
Yeah.
So what I'm doing here is I'm writing. So this is just part of the question, right? This is given in the question, right? So I'm looking for this product, f of x times g of x. That is, by definition, the sum n goes from 0 to infinity of en x to the n. What is en? En is this inner product, or inner, I shouldn't say product, inner sum.
Okay.
Right? So now the question is, like, this can't simplify anymore. I have to figure out what en is. That's my next task, figure out what en is.
Yeah.
So now to figure out what en is, that's why I start using the sum. I put in CK, right? So C doesn't matter which one you call C or which one you call D, but one of the series is, so actually I end up calling this one DN, and I end up calling this one.
Yeah, because which one did you stick with? Were you just on the right side here? Were you just showing that either could be 2 or N? Like
Yeah,
that,
yeah. I
Okay.
showing, and I decided to switch them, right? I decided to not call this C and D. Decided to call it D and C.
Yeah, it was tricking me because I thought you did some cross thing right there. It's like, huh?
Nothing more complicated.
Right,
No,
so-
just switching the position. Yeah.
Okay, so then you did that to find the. You did that, and then what? Because like you have CK DN minus K.
Yeah.
So where did you?
So DN minus K, that'll always be 2. DN is always 2, right? So I just put a 2. And CK, well, CN is N, so CK is K.
How DN minus K is 2?
Well, DN is always 2. For any value of N, it's always 2.
Oh, okay.
So
Yeah,
DN minus K is also 2,
Okay.
right?
Then we just needed to find K.
And then, yeah, exactly. And then I rearranged the sum a little bit. I moved the constant multiple out, and I just have this, which is the sum K goes from 0 to N of K. That has just a formula. That's just this formula. That's just this right here.
Oh, yeah. Okay.
N
that's
from
good.
0 to K,
Yeah.
right? And then, yeah, and that's all we need to do. We just do...
So what happened to the 2? Oh, you canceled it right there.
It cancels here, yeah. It cancels right here. And then that's the answer.
Okay, that makes so much sense. Thank you.
No problem. Let me check the answer quickly.
What's this method called again?
It's called Cauchy Product.
Cauchy. Okay.
Here, it's right here. That's how you spell it.
Oh, okay. Cauchy.
It might be Cauchy. I don't know, but whatever.
The only reason that one was like DN is because it was just 2, right? There was no like X variable on it or anything, or N rather.
Yeah, the reason
Yeah.
DN, like, the
Yeah,
reason
yeah,
this one was
because-
just 2 is because it was just, DN was just defined as 2,
Yeah, okay.
right? This is 83. Yeah. And n plus 1 x to the n goes from... Oh, it's actually n goes from 1 to infinity? It doesn't matter, actually. It doesn't matter what I call it. N goes from... If I start at 0 or 1, it doesn't matter because the 0th term is 0. And the first term is whatever the first term is, so it doesn't matter. Sum goes from n to infinity. And yeah, okay. There we go. Although I'll call it n equals 0, just to be clear. And that's the product. Okay. That is the Cauchy Product section. I think we should move on because I have a feeling that there won't be the Cauchy Product because another professor, I forget which professor, didn't cover it very much.
Didn't teach us this.
Right? So considering...
Interval.
Yeah, that's
Just a
that's a
side
good
note.
question. I don't actually know.
So like, cause like we solved this, but then what of it? What next? Like we just put it in terms of fx times gx. Then what?
Well, now we have an expression for f of x times g of x as a power series, right? We have a
Yeah, that's fair. Okay.
right. That's the whole point is that we now have a way of expressing f of x times g of x as a power series. But
Okay,
yeah,
but yeah,
what interval does it converge on? I don't have an answer. I don't know. I don't even have it written
That's
here.
okay. That's okay.
Okay,
Moving on,
I'll try to
sorry.
figure that out. But yeah, I think we should move on because again, I said I don't think this will be very much on the test.
Do you think they'll have a properties question? I think so. Do you?
I think so. Yes.
I have a feeling there will be 2 questions on this midterm.
Yeah. Okay, the next questions I'm going to do are also are also textbook questions, and we're just going to use these properties, and it's actually the last properties from my notes, and it's about differentiation and the integration of power functions. And I'm going to show it with textbook questions first, because not that the questions here aren't good, it's just that let's see, those are fine. Find power series represent 1 to like 1 minus x. Okay, this works actually. I can do this one from Horace's lectures. So, okay, so if I have some power series centered at a, but just for the example here, I'm centering it at 0. Let's say I have this power series. It converges to f of x on some interval, right? X is between some interval here. Okay. Well, what do I know about f prime of x? I can differentiate each term individually, right? This is going to be, if I just write out a few terms here, it's going to be c0 x to the 0 plus c1 x to the 1 plus c2 x2 plus c3 x cubed, da da da. I can differentiate each term here, right? This is going to be 0. This is, well, I could just say 0 times whatever. It's going to be 0. Plus c1 x to the 1 minus 1 plus c2 x to the 2 minus 1, or I should say 2c2, plus 3c3 x to the 3 minus 1. So term by term, I'm, differentiating each one here. So it's going to be 0 plus c1 plus 2c2x plus 3c3x squared, da da da. And so this is called term by term differentiation. And in general, I can rewrite this as another sum, which is the sum, n goes from 1 to infinity, of n x to the n minus 1, which looks a lot like the power rule, the normal power rule for power functions, because it is, pretty much. It's just inside of the curve.
Is that C3 in like the second last line?
Yeah.
Okay.
That is meant to be C3. Oh, yeah, that is meant to be C3, yeah. Right? And so I can rewrite this f prime as another power series, which is this, right? Cn times n, x to the n minus 1, converges to f prime of x on I. That's term by term. I differentiated it, and I can write it as a new series. It's this series here. And exact same logic for the integration. Term by term integration, it's just power functions. So you can integrate them pretty easily, and they'll converge to this expression here, which again looks a lot like regular integration of power functions. The d is written out in the front here because you don't want to write it here because it's not part of the sum. It's outside of the sum, so it is actually important to write it out there. It's some arbitrary constant. And yeah. So let's see how to use this here. And yeah, so let's give it a try. The first question is find a power series to represent ln absolute value 1 minus x. So we want a power series. We want this to equal a power series. What is the power series? Well, I know that ln absolute value 1 minus x, let's say that's f of x. Well, here I'll say f of x equals ln absolute value 1 minus x. What's f prime of x? F prime of x is negative 1 over 1 minus x. Am I right? Hold on. Did I do that right? Why is there no negative sign? No, there is a negative sign.
Wait, why is there a negative sign?
Because taking the derivative of this, the derivative of ln, so I'll just write side note here, ln, of g of x, ln of g of x prime is g prime of x over g of x, right? So g of x goes on the bottom, the derivative of this is negative 1, so that goes on the top.
Ah, okay, I see, thank you.
Right? So, yeah, it's negative, although that's not in the note here. Oh, no, it's because he does it a little bit of a different way, but that's fine. Anyways, this is... Actually, I'm going to erase this if that's okay. Or I'll just move it to the side. Just move it over here. This can be written as a power series. This can be written as negative, the sum, n goes from 0 to infinity of x to the n. Right? And so now, well, how would I find f of x? I know that f prime of x is the sum, n goes from 0 to negative the sum, x goes from 0 to infinity of x to the n. Well, if I integrate both sides, f of x dx, sorry, f prime, minus, now integrate this side, I'll write it out fully, minus the sum, n goes from 0 to infinity x to the n dx. Okay, well, this left side is f of x. And now I need to figure out, how do I integrate a power series? I can use the property that we just talked about. How do you integrate a power series? Right? So if I, first of all, move that -1 out. Negative the integral sum n goes from 0 to infinity of x to the n dx. This is going to be equal to, f of x is going to be equal to negative. The integral of this is x to the n plus 1 over n plus 1. So still a sum there. Sum n goes from 0 to infinity. And it's plus some arbitrary constant c. Right? Plus some arbitrary constant c outside completely. Now, because it's some arbitrary constant because we're summing together, like it's part of the sum. Doesn't matter how many times it's part of the sum, it's still an arbitrary constant. So we can figure out actually what that arbitrary constant is going to be by plugging in, like we can actually, right now, and I highly recommend it because it gets kind of confusing if you don't do it. Right now, we can figure out that that arbitrary constant is c, is c obviously, but it's 0, because f of 0 should be whatever the side is here, right? Well, what's f of 0? Right? If I use this up here.
0.
Yeah. F of 0 is ln absolute value 1, which is 0. So when I plug in 0 for x, this should equal 0. Well, what happens? I plug in 0 for x here. This is going to be, I'm not going to write it, but this is going to be a 0 here. Right? This is going to turn into a 0. And the whole sum is going to go to 0. So c can't be anything else except 0. Because if c was any other number, this would not equal 0 when x is 0. So I can deduce that c equals 0.
Wait, so C is always going to be f of 0?
Yeah, c is going to be f of 0. That makes sense to me. F of 0. Yeah. That I don't have that in my notes, but that makes sense. That looks right. Unless maybe if your power series is more complicated, that isn't the rule. But here, like if you evaluate your power series at 0 and you get 0, then yes, f of 0 is c.
So wait, what was the original question? The natural log of 1 minus x, right? And we're integrating or differentiating it? Or did you just do both? Actually?
We did both. We differentiated here, and then we integrated backwards because the derivative we can write as a power series, and then we can integrate to go back to the actual function.
Or we're just testing that it works both ways, right? That's what you were doing.
Well, it's you need to do both to solve the question. You need to do both to solve this.
What was the original question then? Like asking?
Find a power series to represent ln 1 minus x.
Okay.
So I don't know how to write f of x as 1 minus x, as a power series, I mean. I don't know how to write f of x as a power series. I do know how to write f prime of x as a power series.
Oh, okay.
So that's,
then we just integrate that.
and then I integrate to go back to f of x, exactly.
Interesting.
When you take the derivative or the integral, does it become n equals 1, or does it really matter?
I think with the integral, it doesn't matter. You don't go lower than 0. If I take the derivative, it doesn't really matter. Just think about what the first few things would be. So like if you're confused if you should include 0 or not, plug in n equals 0, and if your term is 0, then it doesn't matter, right? If your term is 0, like if the term goes to 0 when n is 0, it doesn't matter that if you include 0 or not. If it doesn't go to 0, then you have to start taking into account other things.
Why isn't like a rule? Like isn't if you, because I saw the rule, isn't like, doesn't it say in the rule that n becomes like 1 or no?
Let's see. For differentiation, yes, but for integration, no. So for doing the integral, no. But for differentiation, it doesn't matter, because if n was 0, this would be c0 times 0 x to the -1. So it doesn't matter. It's just 0. You're adding 0. This is an infinite sum, so you're adding 0 because that middle term there is you're multiplying by 0 here. So since you're adding 0, it doesn't matter. You can start at 0. You can start at 1. It doesn't make a difference.
Okay. Do you think they're gonna take marks off for things like that, or no?
I don't think they will.
Okay.
I think we're pretty much done. I just need to move that -1 in. Yeah. So this is just going to be you would write this as -1 n plus 1, -1 over n plus 1, x to the n plus 1. You could reindex if you wanted to, but you don't have to. Which is something that I also have to get to, but yeah.
I was gonna ask what's reindexing again.
Yeah, I'll get to that. Oh, there's another Cauchy product one from the text, which probably is good. And yeah, let's do this one. So first of all, any questions about this question?
Wait, what topic? What part of it was this under? Because we moved from Cauchy Product to this, which is just representing in power series form.
None of this was Cauchy Product. None of this was.
Yeah. I was like, but what was it exactly?
Oh, there's just another problem here with Cauchy Product. For some reason, it's in the middle. There's another Cauchy Product.
And this part was just representing functions in
as a power series. Yeah.
Okay.
Which is the whole point of power series, which is why we do 6.3, which is to represent in general any function as a power series. With some limitations on that, but still, that's kind of the point, is that we want to be able to represent any function as a power series, and so this is sort of getting into that. Some simple ways, and then the Taylor and the Maclaurin series are the ways to do for any function. Okay, the next one is an interesting one. It's a way. So first of all, let me write the question. Evaluate the sum. N goes from 0 to infinity of n over 3 to the n. So if I just stop the question here, it would be very hard, right? But I'm gonna the rest of the question is as f prime of 1/3, where f of x equals the sum n goes from 0 to infinity of x to the n. Because what you're supposed to notice here, if this wasn't here, if this wasn't part of the question, what you would have to notice is that this is a function f of 3, right, or call f of 1/3, which is n equals 0. So it's n times x to the n. Right? Do you see that? That's the same thing. I just wrote it as a function of x. Right? So what we want to do, this gives us the hint here, is that it is a function of x. This is the function. This is the derivative. Right? That's the hint they're giving us. This is the derivative, actually. This is f prime. Right? And so what would the actual function be? Well, that's what we're gonna have to figure out here. Okay, so what would the actual function be, and then evaluate that at 1/3. Evaluate f prime at 1/3, and that'll give you the sum here. So what we want to know is that what we have to know. Yeah?
Is this Cauchy Product?
No, this isn't Cauchy Product. We're not. Cauchy Product is you're multiplying two different functions, right?
Right.
Don't worry. So what we know is that f prime of 1/3 is our series, right? F prime of 1/3 is our series. So first of all, f prime of 1/3 is our series. So I want to find what. Yeah. If I integrate both sides here, f prime of 1/3 dx equals integral of the sum, n goes from 0 to infinity of n over, yeah, this is weird to do. Sorry, let me write this as.
Wait, how do we know that the n over 3 is not fx? Because I'm a bit confused with that one.
Well, it says evaluate this as this. This is this.
As that's the value. Okay.
Right?
I can't.
It is that, right? So in general, f prime of x equals the sum n over the n's to infinity of n x to the n. So now we integrate. The integral, let me make sure I'm doing this right. Don't want to make a mistake. Da-da. So f prime of a third. Okay, this isn't wrong what I'm doing, but I think it's going to get us not directly to the answer. So let me do what Orwith did, and it's going to get us more directly to the answer. This is what we know, right? We know this right here. We also know now that f of x equals the sum n goes from 0 to infinity of x to the n. What's f prime of x? F prime of x is the sum n goes from 0 to infinity of n x to the n minus 1. Right? So right now, if I evaluate this at f prime of a third, right, we're gonna get the sum n goes from 0 to infinity of n over 3 to the n minus 1. Right? Which is equivalently f prime of a third equals 3 times the sum n equals 0 to infinity of n over 3 to the n. Right? Yeah, we're good, don't worry. So I know that this sum, I can rewrite it 1/3 f prime of a third equals the sum that we're looking for. N over 3 to the n. Remember, that's the sum we're looking for. We're looking for n over 3 to the n over 3 to the n. We now have an expression for it, 1/3 f prime of 1/3. Right? Let me make sure that's right. Yep, we're good. 1/3 f prime of 1/3. Now, if I can figure out what 1/3 f prime of 1/3 is, then I evaluated this sum. I know that the sum is equal to it. If I can just find what f prime 1/3 f prime of 1/3 is. So what's 1/3 f prime of 1/3? Well, I can go back to our function. I know our function, f of x, is 1 over 1 minus x.
Wait, don't we already know what f? Because it isn't in square. Can't you use that or no?
Where
We always said f prime 1 over 3 equals that. Can we not use that?
like sub this in?
Yeah.
Well, what would happen is that you'd get the sum here, and then that wouldn't really be helpful because you'd know that 1/3 times that sum equals that sum. Oops. Which wouldn't be true, because then you'd get that 1/3 equals 1. So it seems like, hold on.
But like, what's wrong? Because like, I'm just trying. Like, why couldn't we not do that?
Then well, because hold on. This might actually be wrong.
I don't even get what the question's asking.
This might be wrong to say that here.
What's the question asking?
The question's asking, the question is, what is this series is going to converge to something, right? Figure out what it is, evaluate what it converges to, by calling it f prime of 1/3, right? Or technically, actually, because of the wording, you're right. The wording here, that doesn't mean that this equals f prime of 1/3. I'm realizing now. It just means that it's something related to f prime of 1/3, where f of x is x to the n. So sum n equals 0, x to the n. Right? So the whole point of the question is to get something like this right here, to get something like this step, where we're showing that the sum we're looking for is equal to something we can actually calculate. 1/3 f prime of 1/3.
Oh.
That's the whole point. Is this step right here, to write it as something we can actually calculate. And I can calculate it because I know f of x is 1 over 1 minus x. I know f prime of x is is just 1 over 1 minus x squared.
Yep.
F prime of a third is 1 over 1 minus a third squared, which is going to be 1 over 2/3 squared.
9 over 4.
Yeah, 9 over 4. Right?
Okay, yeah, that makes more sense. Okay.
Right? So I know now that 1/3 times 9 over 4 equals the sum. 3 to the n, right? And so 3 over 4 is our answer. This sum, this infinite series, will converge to 3 over 4.
So before we were more so calculating if a series would converge or not.
Yeah.
But since for power functions, they will converge. Like
we
it's
know
guaranteed that they will
what
converge.
they're going to converge to some function, right?
Mm-hmm. And then we're just calculating the actual value that it converges to.
Yeah.
Okay.
Yeah. But the trick is to represent these power series as integrals and derivatives of the functions.
Yeah, I'm not gonna lie.
Yeah,
I'll
makes
actually
sense.
run through this question once more.
Yeah,
Honestly.
for sure.
Yeah.
I'm just going to erase this
That's
because
different.
yeah, this, let me erase this. It's not that it's fully wrong. I mean, it is wrong. It's not equal, but based on the wording of the question, yeah. So evaluate this infinite series, find what it converges to, exactly the number, by treating it as f prime, some multiple, I should say af prime or something, some multiple or something happening to f prime of a third, right? Because notice it's similar, it's very similar to n x to the n, it's just that it's evaluated at a third, right? If I had n x to the n and evaluate that at a third, it would be n over 3 to the n. So it is a power function, power series I mean, it's just evaluated at 1/3. So this is where I started. I take the function. So again, I'm trying to find an expression for this infinite series in terms of something I can actually calculate. So I know that f of x is that. The derivative is that. The derivative evaluated at a third is that. And then a little bit of rearranging. The -1 turns into a 3 in the numerator, which turns into a 1/3 in the front here. We get that 1/3 f prime of a third equals the exact series we're looking for.
But how did we get the 1/3 again?
In the front here?
Yeah.
Well, from
Like,
this
how did we?
this 3.
Oh, because we took a 3.
Yeah, from that 3.
We did a, what was it called again? Change the index, I think. Did we? Or...
We didn't change the index. No. We just what happened is that this denominator is 3n minus 1, right? 3 to the power of n minus 1, which is the same thing as 3 to the power of n, 3 to the power of minus 1, which is the same thing as 3 up here, 3 to the 1.
3 to the n minus 1?
Yeah, 3 to the n minus 1.
Oh.
Because this is f prime of x, and I just evaluated that at 1/3, not at 3, at 1/3. So it would just go in the denominator. And yeah, so this n minus 1 turns into a 3 to the minus 1, which turns into a 3 to the 1 in the numerator, which can come out, which can then go out here as a third.
So wait, so we said it in the form of like the differentiation, which is x n minus 1, and then we moved on to say that based on what we were given, we're trying to solve for it in like this was the original thing, right? N over 3 n minus 1.
Yeah.
Right? And we set it in the form of the actual derivative. Then we just solve at 1/3.
We set it equal to like we evaluated at 1/3. Yeah.
All right. Then what's next then exactly?
Yeah. So we got this. We got this equation: 1/3 f prime of 1/3 equals this series, this infinite series, right?
Yeah.
Well, this I can calculate, right? This I can calculate. This is something that I can figure out. I can go back up to the top. F of x was this series. This series is 1 over 1 minus x for absolute value x less than 1, but that doesn't particularly matter right now. X is less than 1, so we're good. Right? Everything we're evaluating is less than 1. So f prime of x is 1 over 1 minus x squared, right? F prime of a third is what we need, so f prime of a third is 9 over 4. So 1/3 times 9 over 4 equals the series. 3/4 equals the series.
Wait. Can you scroll up a bit on the right side again? Let me just. So after we basically found what the original function would be based in terms of like n x and minus 1. So it'd have to have been x to the n. and then we set that to the original like f of x, right?
Yeah, it tells us f of x is this infinite series.
Oh, they okay.
They
and
give
then,
us f of x is this infinite series.
Oh, I thought. Okay.
Right?
And then we just keep going. Okay, yeah, makes sense.
Right?
Yes.
So this is there was a couple of these in the homework, and they were pretty good questions.
Wait, what was the final answer? Can you scroll down?
Yeah.
No, we just put it back into this and get that. Okay.
Okay, and the last thing, which I didn't talk about yet, and I realized I didn't do it in the order. I didn't talk about reindexing. Let's just check mark off everything we did. So we did that. Didn't do reindexing, Cauchy product, and derivative and integrals. Reindexing is an important thing to be able to do, and also confusing. So let me give it a shot. I'm gonna find quickly what question. Hold on 1 second here. I'm gonna find exactly what questions in the homework. What'd you say?
The screen is very trippy.
Yes, that's why I put it on. I want to see exactly which questions I used reindexing for.
Gotta love the infinity screen.
Who doesn't, you know?
Oh yeah, 79, and
It converges to a point.
it does converge to a point. Okay,
You wonder what
79 and
infinite-
81.
Infinitely small
This is
point.
how we clone humans, guys. We do this.
For long enough? Yeah.
You know what?
We did
Like,
83.
and if you have to go into the start of the computer and go into the end, what would you find at the end? Gold, money, fame.
Did you say at the end of the rainbow?
Like, you know, there's your path, kind of. What would you find?
Oh. I was going to say something smart. You said something at the end of the rainbow.
No rainbow.
No rainbow, damn it.
Okay, let's give 79 a try from the textbook. Remember it being a good question. And it needs reindexing. That's why, in particular I'm doing it, but it doesn't need. No, actually, it does need to be reindexed. So the question is saying, in the following exercises, express the sum of each power series in terms of a geometric series, and then express the sum as a rational function. So turn this infinite sum into a geometric series, then turn that geometric series into a rational function. Right? So the infinite series we have, I'm going to write it out, is x plus x squared minus x cubed plus x to the 4 plus x to the 5 minus x to the 6. So essentially, every third item is negative. What we can call this then is we can call this the sum, and since the hint is group powers of 3k, 3k minus 1, 3k minus 2. So this would be a 3k, right? This is 3k. Sorry, x to the 3k, I mean. X to the 3k. These would be the x to the 3k minus 1. And these would be the x to the 3k minus 2. Well, I can write this as a sum. Right? Come on. There. The sum, n goes from 0 to infinity of, well, this first one is x to the 3n minus 2. K or n, doesn't matter what you call it. I'll use k here. Plus x to the 3n minus 1 minus x to the 3n. And you can check. You can try, like, type plug in n equals 0. So that's, oh, that's not good. That is not, hold on. 3k, 0 times 3k. Because if I plug in 0 now, oh, it doesn't start at 0, it starts at 1 then. So yeah, so look, what happened is that if I start at 0, this is going to be x to the negative 2, x to the negative 1, x to the 0, which is not part of the series. If I start at 1, x to the 1, x squared, x cubed. And the next one would be n equals 2. It would be x to the 4, x to the 5, x to the 6. Yeah. So we started 1 here. That is the reason that this is going to become a reindexing problem. So we'll get to that in a second. Okay, so now we need to write this as a geometric series, which starts at, like, which can then be written as a rational function. So the first thing to note is that a geometric series always starts at an index of 0. Index of 0, n equals 0. We need to fix that. We don't want to start at 1, we want to start at 0. Let me open a new window here so I can look at the solution I did before, just in case I don't want to screw anything up. Yeah. I'm going to have to re-index. Oh, not immersive reader. Is it going to talk? Okay, hold on. So I'm going to have to re-index. So the re-indexing that I'm going to do is that I want this but I want this index variable to start at 0. It's going to be some other variable, right? So let's take a look at that equation down there. N equals 1. I want this right side to be 0. So I'm going to subtract 1 from both sides, and minus 1 equals 0. Now I'm going to define a brand new variable that we haven't used, right? That's not part of this question, k, to be n minus 1. Because then, if you combine these two equations, we get k equals 0. K is now an index variable, right? K is an index variable that starts at 0, which is what we want. And we just have to adjust everything else to account for this. And to do that, you rearrange here. So this is our equation 1, this is our equation 2, this is our equation 3, this is our equation 4, and then we have equation 5, which is that n equals k plus 1. And so how you adjust this is you take the sum. The sum is going to go from k equals 0 now. Okay, k equals 0. And everywhere you see an n, replace it with k plus 1. That's it. X to the 3 k plus 1 minus 2, right, plus x to the 3 k plus 1 minus 1 plus x to the 3 k plus 1. Sorry, sum to infinity. You don't have to worry about the upper bound because we did reindex in MTH 140, but you had to worry about an upper bound there. Here you don't have to worry about upper bound. It's just k equals 0, the lower bound there. And so now I reindexed, and now k equals 0 to infinity. This is going to be x to the 3k plus 3 minus 2 plus x to the 3k plus 3 minus 1 plus x to the 3k plus 3, okay, which is going to be the sum. K goes from 0 to infinity of x to the 3k plus 1 plus x to the 3k plus 2 plus x to the 3k plus 3, right? So now the sum operator, remember the sum, this should have been a minus. It's a minus from the top part here. It's a minus there. Remember the sum operator is preserved under addition and subtraction. So what that means is we can do this, k equals 0 to infinity. So actually, we didn't have to reindex right there. We could have reindexed a little later, but we would have to do a bunch of separate reindexing. The same reindexing, but it would be a bunch of separate ones, so that's why I decided to do it there. But this is just going to be k plus 1 plus the sum. K goes from 0 to infinity of x to the 3k plus 2 minus the sum. K goes from 0 to infinity of x to the 3k plus 3. Okay, before I move on, we now have 3 separate almost geometric series that I can quickly turn into rational functions. Before I move on, reindexing. Any questions about exactly how I reindexed here so that I could turn this into
Two questions.
this?
Yeah.
Yeah.
You said something about reindexing now instead of having to do a lot more reindexing later. What are we talking about? Because I could get the n equal 1. You said it's k, whatever.
Because if I had here n equals 1, n equals 1, n equals 1, which I could have totally gotten to here just as easily, Yeah, I mean, I'd have to re-index 3 different series now, and you technically have to write everything out. But it doesn't really matter. Like, you could just say k equals n minus 1, and, you know, it would be just as easy. This is all I mean, is this, right? So instead of 3 series re-indexing, but again, it's re-indexing in the exact same way for 3 simple series, so it wouldn't be much harder. Yeah, this arrow is a little bit misleading. You could have gotten to here without re-indexing. It's just that to do the next step, you'd have to re-index, and for me, it was more convenient to re-index up here.
Okay.
That's why.
Right.
Okay. Any other?
Question.
Yeah.
Yeah. It's just an off-topic one, really.
Sure.
Are you gonna go straight to 830 and just finish?
Yeah, I guess so.
Okay. Also, if you write your K's like this, how do you write your linear density? Just
well, my K's are like this, and my mu's are like this. So.
Dude, that's okay.
So.
Okay. Just off topic. All right,
yeah.
Okay. I was just curious.
Yeah. Anyways, that's the best. The best you'll get out of me is like that as a K. So mu is a little shorter and a little curvier. So there you go.
I see.
Yeah.
Wait, try to write it like.
Properly?
Yes.
Okay.
Try it.
K and mu. There we go.
I'm just not used to it. Used to pure K's. I like it.
Yeah, the K. I have to lift up my hand 3 times to draw this.
Yeah.
One letter.
We're about efficiency.
Not gonna do that. Not gonna do that. So I'm gonna do that instead for K.
I was curious, man. I was like, what do you do in your physics when you're,
Yeah.
you know?
Luckily,
Alright,
there's no
all.
K's in physics. It's just the mu, so I don't really get confused.
Yeah. Sorry about that.
Don't worry. Okay, so now we can carry on from here. This is going to be the sum. K goes from 0 to infinity of x to the 3k, plus the sum n goes from 0 to infinity of x squared x to the 3k, minus the sum. Sorry, that should be k goes from 0. K goes from 0 to infinity of x cubed x to the 3k, right? I'm getting a phone call for some reason. Don't know why. Not from a no caller ID. The x constants can come out, right? X squared, x cubed can come out of the sum. And then the powers here, well, I can actually kind of factor out the sum, right? So I can write this as x plus x squared minus x cubed times the sum. K goes from 0 to infinity of x cubed to the k. Right, I kind of just factored out each term here has that sum. So I can do that. And that I can write as a nice rational function. X squared minus x cubed times 1 over 1 minus x cubed. So the final answer is x plus x squared minus x cubed over 1 minus x cubed. So this original sum is equal to this rational function.
Could you go to the fourth last step?
Fourth last step here?
Yeah, right there. Okay. So with the whole numbers, the integers, you just factor out the x, and then 3k, factor that out. Okay, yeah, got it.
Good. No problem. Okay, any more questions about this one?
Wait, once you factor that out, right?
Yeah.
Isn't it 3 times that series?
Well, tell me this. If I have like 2a plus 3a plus 4a, and I factor out the a, right? It's going to be 2 plus 3 plus 4 times a.
Yeah. Yeah.
Not times 3a. Just times a.
I didn't mean to multiply that by that, but you know how you have the same series added 3 times, isn't it 3 times that series?
Like,
because then you made it into 1.
Like this series here, it's exactly the same as what I just this right here. I just factored out, like, just the same as you factor out an A here, right? I
Yeah.
factored out this series, which exists in 3 different spots. It exists here, exists
okay. I was
here,
thinking you factored out the thing. Okay, yeah. Yeah, that makes sense.
right? Yeah. So yeah. Okay. I have one more good question, number 95. I actually didn't get the exact answer from the textbook, but and off by a negative. So let's see if I do it again. Maybe I'll also be off by a negative. Any more Horowitz questions? Let me just look through them really quickly. There's another Cauchy product, but I think maybe we'll do that at the end if there's nothing else to do. Effectively doing one more of those. Doing. That's fine. That's fine. That's fine. Product. Oh, and this is here. Fine. Okay. I have one more Horowitz question that I'd like to do. Yeah, let's do this Horowitz question. So it is write. I'll type it. Write the following function as a power series. Right? Let me just make sure that that's what it is. Yep. Or find a power series to represent the following function. So f of x equals tan inverse x. Tan inverse x. Okay, so we want a power series that represents this function. Well, one thing we know is that f prime of x is 1 over 1 plus x squared. Right? That's tan inverse. That's the derivative of tan inverse, I think. Can someone make it extra sure that that's right? Yeah, that looks right to me. This can be written as 1 over 1 minus x squared, which can be written as the sum, n goes from 0 to infinity, of negative x squared to the n. So we know that f prime of x is the sum, n goes from 0 to infinity, of negative x squared to the n. So to find what f of x is, I integrate both sides. Right? So I'm going to find that f of x, which is what we're looking for, is this power series. Now, what's the power series? The integral, this is a convergent sum. Since this is a convergent sum, I can switch the integral and the sum. So I can say that this is n equals 0 to infinity. If you don't know, or it's not convergent, well, if it's not convergent, you can't. If you don't know, you can pretty much just pretend like you are, but don't actually write it. And it works the same. But since this is notably convergent, I'm allowed to actually write this. Negative x. So it's going to be negative 1 to the n x to the 2n dx. Negative 1 to the n can come out of the integral, but not of the sum. And now I just integrate x to the 2n, integral of x to the 2n dx. So f of x equals the sum, n goes from 0 to infinity, of negative 1 to the n, x to the 2n plus 1 over 2n plus 1, plus some arbitrary constant c. And f of 0 should be whatever f of 0 is, right? So what's f of 0? Well, tan inverse of 0 is 0. So when I plug in f of 0, I should get 0. So let's see. What happens if I put x equals 0 in here? This whole thing goes to 0. So that means that c equals 0. Right? So f of x is just the sum, n goes from 0 to infinity, of negative 1 to the n over 2n plus 1, x to the 2n plus 1, And yeah, that's it. Yep. The trick to do this step here is just sub in what it's centered at. So if it was centered at a different value, you'd sub in whatever that is. You'd say f of a equals that. And then, yeah, okay, so then actually I think in general, a better rule is that f of a equals c. I'm pretty sure that's always right. Although I'm not entirely sure, I'm pretty sure this is always true.
So you mean that whenever you put in that a, we get a 0 for the value?
We get this because the actual power series should go to 0, and all you have left is f of a equals c, equals 0 plus c,
That makes sense.
right? So I can't say that this is, like, I didn't hear a professor say it, so I don't know. I didn't hear the textbook say it either, but that seems right to me. So take it as you will. But anyways, that's the answer down here. So tan inverse x, another way to write that if you wanted to and you had infinite amount of time, you could sit here and evaluate it like this as an infinite series. Okay, that's the last Horowitz problem. Other than the Cauchy product one, which I think I'll do once I'm finished the other textbook questions I want to do. There are other 6.2 questions here, but I think that's okay. They're not much different. I would like to do this textbook problem that I had. Took a little bit of time. 95? What about 93? I remember 93. Okay, we'll do 93 and 95, and 69 was 1, 2. Yeah.
Can you go to the top of this question?
Sure. Here. Do people want to see another re-indexing question?
Come on, people. Did you want to see this?
Do we see
Actually, I want to see that other one, the first one done again, because I kind of still don't get it.
Well, how about I do another re-indexing one and see if it makes more sense the second time I do it.
Okay.
Okay. So, question 69 from the book is write this as a rational function. That's it. Write this as it's actually a pretty simple question. It's just that you have to re-index to do it. So that's why it's a little complicated. So we have our sum. N goes from 1 to infinity of 1 over x to the n, right? Which can also be written as 1 over x to the n, like that, right? That's equivalent. This would be equal to 1 over 1 minus 1 over x. This is actually the example I use in my notes to show re-indexing, so it's good that I'm going over it. This would be equal to this if this started at 0. But it doesn't start at 0, so it doesn't equal this. Now, technically, I guess you can account for this by just doing, well, what if by there would be another way to account for this, but one way to account for it is by re-indexing.
Why is it like, does it matter between the 0 and the 1?
Well, because the definition of the convergence of because by using this rule, you're using this fact. You're using the fact that the sum n goes to 0 of a x to the n equals a over 1 minus x, right? This is only true for, first of all, absolute value of x less than 1, but also the series has to be exactly this.
Yeah, in that form. Okay.
Right?
Yeah.
Right, it would be a different sum because this is an exact number, 1 minus x. The a over 1 minus x, that's an exact number. So changing where you start, that changes the result.
Yeah.
Right? So this isn't equal to this, but after re-indexing, it will be. So I look at the index, n equals 1. I want this value to be 0, so I'm going to subtract 1 from both sides. I'm going to define a new number k to be n minus 1, a new variable k to be n minus 1. Which will let me combine these two to say k equals 0. Right? Now what do I get from this? I get that n equals k plus 1. So plugging in all this, usually how I write this is n minus 1, k equals n minus 1, n equals k plus 1. That's how I would do it in my notes. I just write those two lines, and then Wow, the N's and the K's are looking a little similar. But yeah, I just write those two and put those
Slow
together.
down a bit. Webcam blocking.
These two. Like that. So that means that I can equivalently write this series as k equals 0 to infinity of 1 over x to the k plus 1. Which means 1 over x to the k times 1 over x. Which means 1 over x, I'll just move it out, 1 over x out here. This is 1 over 1 minus 1 over x, but you have to multiply by 1 over x. So that'll get me 1 over x minus 1. And that's our final answer. So I had to reindex. Reindexing got me another term out here. So it's not just a writing trick. It's a trick to actually get the answer. Right? Like it's going to actually change the answer by changing the index. Because it doesn't change, like this value is still the answer to this. It's just that to get there, to apply the rule you want, you have to manipulate it in some way. And by manipulating it, you're getting an extra product there. You're getting an extra multiplication of 1 over x. Or dividing by x, or however you want to say it.
Can you explain that? Like, I didn't get how it moved. Like, how did you get an extra 1 over x?
So, does this make sense? Going like this?
Actually, yeah.
This step here, like the sum k equals 0 to infinity.
Yeah. No, it makes complete sense.
Right? And then now this is 1 over x. And now this is 1 over x.
Yeah, that makes sense. Yeah, sorry.
So this is how it arrived after the reindexing, and then you manipulate it to get it here. And then this turns into that. Right, let me highlight that nicely. This turns into that, and this just stays out front, right? And then you multiply them and you get 1 over x minus 1. Okay.
So the final answer is just 1 over 1 minus x.
The answer is 1 over 1 minus x. That's this series.
That's 1.
What'd you say, sorry?
1 over x. Because I said 1 minus x. I meant x minus 1.
So yeah, whatever I wrote here. 1 over x minus 1, yeah.
Yeah. This was actually the one that I had a problem with. It was the one with the... I think it was reindexing as well, but you just had so many terms.
This last one up here? This reindexing one?
Yeah.
Yeah,
I think
this
one. I kind of... I mean, I guess if the same rules apply, but man, like starting from how the question asked for it was a bit confusing.
Yeah. No, I see.
So unless you have another question first, yeah.
Well, I have another one that's similar. It's actually pretty much the exact same question, just with different. It's just like doing it all over again, but with a different series. So maybe let's try that. Number 81. It's really the same question. It's just a different initial series they give us. So number 8.
Honestly, I feel like it's something I feel like you'd see in the final exam, but not the mini test. Like I feel like. So we don't really have to get into it if you have other questions. Like you could do some out questions.
Maybe I'll do all of it except the reindexing part a little bit quickly. The reindexing part I'll go slow, but the rest of it I'll go a little bit quickly. So it's the same question. Represent this infinite sum as a rational function. First as a geometric series, then as a rational function. And the hint that they give is group powers of same hint as before. So group the powers of 3. So in general you can write this, so group powers of x to the 3k, x to the 3k minus 1, x to the 3k minus 2. So this would be
it is 3k.
Good, yeah. So this would be the 3Ks. This would be maybe I'll highlight it like that. These would be the 3K minus 1s. And these would be the 3K minus 2s. Because they're 2 off from a multiple of 3. Also technically 1 off from a multiple of 3, but that doesn't matter. they're two lower than a multiple of 3 is a better way of saying it. So this is the sum. K goes from 1 to infinity of x to the 3k, or not actually, x to the 3k minus 2 minus x to the 3k minus 1 plus x to the 3k. Okay, I'm going to ignore the reindexing for now. I'll do it a little later just so that, because this is to explain reindexing. The sum operator is preserved under addition and subtraction, so we can say the sum k equals 1 to infinity of x to the 3k minus 2 plus, well, minus. The sum k goes from 1 to infinity of x to the 3k minus 1 plus the sum n goes from, k goes from 1 to infinity of x to the 3k. Am I going to have trouble? No. Let me look at my... I solved this before, so I can look at my notes, but... oh, yeah. It'll be fine. So I have 3 sums now. I can simplify a little bit. But simplifying now would cause problems. Oh, no, it wouldn't cause problems. It's okay. So this minus 2 is the same thing as writing 1 over x squared. This is the same thing as writing 1 over x. Nothing there. So I can pull those to the front. 1 over x squared. 1 over x. And now I have a bunch of these series. So I can write this again. I can factor out that series. So it's 1 over x squared minus 1 over x plus 1 times the sum k goes from 1 to infinity of x to the x cubed to the k. Now again, you would like to say that this is 1 over 1 minus x cubed, but you can't because the sum doesn't start at 0. So you can reindex. So reindex. So to reindex, I'm going to look at my thing here, k equals 1. I want this side to be 0, so I'm going to say I'm going to subtract 1 from both sides. I'm going to define a new variable n, or I'll not use n because whatever. I'll use something that's a. I'll use a or b. I'll use a. A is k minus 1. So combining these two, I get that a equals 0. That's my starting index. And k equals a plus 1. So I can rewrite this sum as 1 over x squared minus 1 over x plus 1 times the sum. A goes from 0 to infinity of x cubed times a plus 1, which now can be written as x cubed to the a, x cubed. X cubed can come to the front. Oops, x cubed can come to the front, right? X cubed can come to the front like that. Then we have 1 over, so I'm going to multiply the x cubed in. This is going to be x minus x squared plus x cubed, right? That can now evaluate to 1 over 1 minus x cubed. And so our final answer is x minus x squared plus x cubed over 1 minus x cubed. So I'm going to focus on the reindexing part here. I did it with less terms this time. Like I on purpose, I split it up into, I'm going to sneeze. Okay, I split it up into just like one infinite series that we have to reindex, and it's at the end instead of at the start.
I didn't even notice that. I was just like, okay.
Yeah. So, did that make sense, the reindexing here?
I mean, like, I get the purpose of it since this summation has to start at 0. And I think the problem I had with the first one is actually the fact that each of them change rather than just having the plus 1 at the end with the summation and then just having the...
yeah, I did it a little bit of a... I did it a different time in the question, so I thought it would be good to do it at this time in the question.
I actually like this better.
Yeah,
it
good.
Makes, yeah. But why didn't you use n? Is n arbitrary or is it just...
Like, why did I use a instead of n?
Yeah.
I just
and
didn't.
it's
If I said
funny.
n, people you might get confused.
get
Which one's the one that
confused,
I'm
yeah.
replacing? Maybe you think that
Yeah,
k is the
yeah.
one I'm replacing n with.
Okay. Yeah,
I just
that
didn't
makes
wanted
sense
to
now.
avoid some confusion. So yeah,
All right, that makes sense. All right, end with something that we can't solve, like how we always do.
something that we can't solve. So we get
Yeah, that's
Well, what
just
else do I have? This was 90. Oh, this was 85. 93 we haven't done. 95. Oh yeah, 95 is the one that I wanted to do. Let me see this quickly. So which one do you want to do? You can decide. Here, I'll put both of them on the thing and people can decide.
let's see.
There's
Which one seems less likely to be solved? This one.
95 I did, but I got the answer off by -1.
Well, let's see why you got the answer off by -1 then.
Well, yeah, okay. We can do that. So it looks like we're going to do 95. But these are the two questions. I can do both. It's okay. Like, I can do both of them. I don't mind.
Sure. Sure.
And, yeah, I guess that why not just do both of them? So let's do 93 to begin with, and then we'll do that. So 93 is one of those where you evaluate something, the series, as a derivative at a specific value here. Right? Where f of x is x to the n.
Wait, is that a second derivative or n?
Second derivative. Second derivative.
Oh,
second
wow. Nice.
Don't worry. Don't worry. Okay, so we want to evaluate. We want to say that the sum n equals 2 to infinity of n minus 1 over 2 to the n is something. Specifically, something relating to f double prime of a half. Right? So we start here. F of x equals the sum n goes from 0 to infinity of x to the n. Okay. What would f prime of x be? F prime of x is the sum n goes from 0 to infinity of n x to the n minus 1. And what would f double prime of x be? Well, it would be the sum n goes from 0 to infinity of n minus 1 x to the n minus 2. Okay. It tells us evaluate as f prime of a half. So let's plug in a half here. F double prime of a half. So what's f double prime of a half? Well, sum n goes from infinity to 0, or 0 to infinity of, okay, it's going to be of a half. So n minus 1 over 2 to the n minus 2. Right? Evaluated a half. Okay, it's very close to what we want. n minus 1 over 2n. 2 to the n. We also
Very
started
close to what?
very close to what we're trying to evaluate. This was our goal. We're trying to evaluate.
So we're trying to make, when it says evaluate, we're like making sure that it's actually the same.
No, it means find the actual, what exactly does this converge to? What exact value does that converge to?
Okay.
It's an infinite series, but it'll converge.
Just like some questions we weren't finding the convergence, and like, are the interval of convergence? I was like, what exactly are we doing?
So
But,
here we're looking for the exact number that this converges to. The exact number that this converges to.
Okay.
Right? So we can do that because we know that it is a second derivative of, or it's somehow related to the second derivative of f.
Okay.
So now that I take the second derivative, I have n minus 1 over 2 to the n minus 2. So that turns into 2 to the minus 2, which turns into 2 to the 2, which turns into 2 to the 2, which turns... where'd my sum go? Which turns into 1 over 4. Did that make sense? All the jumps I took there? Minus 2, 2 to the minus 2, 2 to the 2, 2 to the 2. Oops. Come on. And then it would be 1 over 2 to the 2, which is 1 over 4. Now we know that our infinite series, the exact thing we're looking for, is equal to 1/4 of f double prime of a half. I can find f double prime of a half because f of x, directly from this, is 1 over 1 minus x. F prime of x is 1 over 1 minus x squared. And f double prime of x is 2 over 1 minus x cubed. So now I just have to say, okay, well, what's f double prime of a half? That's 2 over 1 minus a half cubed, which is 2 over a half cubed, right? Which is 16. Yep. Which is 16. So I know that 1/4 of 16 equals the sum we're looking for. Sorry, it's actually not exactly the sum we're looking for, and I'll explain it in 1 second why it's not. But I get a value of this series to be 4. Now, is that the series that we were looking for? It almost is. But one thing to note is that the lower bound, the starting of n is 2 here, and starting of n is 0. Does that matter? What happens for the n equals 0 term? When n equals 0, this is 0, it's all 0. We're adding 0. When n equals 1, this is 0. Oops. When n equals 1, this is 0. This whole thing's 0. We're adding 0. When n equals 2, nothing's 0. So, but that doesn't matter. So we start at 2, right? Which is the same thing. I just want to see that this is the same thing. Starting at 0 is the same thing as starting at 1, because the 0 term adds 0. And starting at 1 is the same thing as starting at 2. Starting at 2 is not the same thing as starting at 3, though. Because when n equals 2, this is a value. This has a value that's not 0. Right?
Wait, you said n equal 2 is also n equal, same as n equal 1?
N equals, yeah, n equals, so start at 0. N equals 0 is the same as n equals 1. N equals 1 is the same as n equals 2. But n equals 2 is not the same as n equals 3.
Oh, wouldn't you have like 2 minus 1 times something here?
Yeah,
Ooh.
because for 2, you'd have 2 minus 1 over 2 to the 2. That's not equal to 0, right?
Okay.
So we can't just start at 3 as if nothing's happening, because we're going to lose this amount.
Oh, I thought you said equals to 0. Okay, yeah.
Right? We'd lose this amount, right? If we just started at 3, so we can't do that. But 0 minus 1 over 2 to the 0, that does equal 0. And 1 minus 1 over 2 to the 1, that also equals 0. This is for n equals 0. This is for n equals 1. So since both of those sums are 0, since both of those, those terms are 0, you're just adding 0. They don't add anything to the actual infinite sum. So I can just start at 2.
Yeah, I get it. At first, how you were saying it, I thought you were saying like 1 is the same thing as starting at 2. I'm like, no, it's not 1, 0. 2 is a value. But I get what you're saying now.
Yeah.
Yeah, that makes sense. So wait, we found, basically we actually had to find the f prime at half to put back into this value.
Yeah.
Which we also equated to the powers, to
Yeah.
the, well, it's a power. Well, no, it's a summation.
It's just an infinite series. Yeah, it's just an infinite series.
Yeah. And then we kind of just did some move. Yeah, we got 4 equal to that. Then we solve for it. Can you scroll down for a sec?
Yes. That's the end.
Oh, okay. So,
sorry.
Is it just equal to 4? What next?
That's it. The answer's 4.
That's it. Okay.
The answer's 4. We evaluated. We saw that series is equal to 4.
Okay.
Right, and yeah, that's it. So there are methods to actually find exactly what values do these infinite sums converge to. It's just a lot of them are very advanced that you don't talk about ever as an engineer. You don't talk about ever. But there are a lot of methods.
Mathematicians.
What'd you say?
We leave those to the mathematicians who actually concern themselves with the nitty gritty. They're like, actually, yeah.
Well,
we don't do proofs in engineering.
Yeah, we don't do proofs.
In none of our math classes do we do proofs.
Never. We leave those to the M in STEM.
Yeah.
The E.
Not my major.
Well, like
not my major.
For example, we know that the sum, because I'm gonna talk about math now, just for a second. The sum n
serious taboo.
N goes from 1 to infinity of 1 over n squared. Okay, does this converge? Yeah, it converges. We know how to show that this converges, but what does it converge to? Right? Well, it actually converges to pi squared over 6. Exactly.
That's beautiful.
And it's weird. It doesn't seem like it should converge to anything relating to pi. I'm quite certain there's a 3 blue 1 brown video about this. I forget.
There is.
There is?
That guy, man.
Yes.
So
Adam,
yeah.
Here's the problem that I have. Here's the problem that I have with this proof. Because I watched it too, right? And they say, like, if you know when you take the alternating series of 1, -1, 1, -1,
Yeah.
right? They have that as an average value of 1 over 2.
Yeah.
Which doesn't make sense to me.
Yeah, no, that's a like a hand wavy way of dealing with infinite sums. That's not a very
So they actually used that to prove that, like, that was one way. Using that in another series was one way of proving this.
Yeah. No. It just works. That's just like lucky that it worked, even though you made that mistake. It still ended up working out, right? It's like, yeah, it's not right to say that it's equal to a half, but I guess in some sense, and in enough, it makes enough sense to prove the rest of this. In an actual formal setting, no, that wouldn't be okay.
Wait, what? What equals a half? You guys went a little bit over my.
You'd have to watch the video. What all they're saying is that the infinite, like, they use the fact that the infinite sum, n goes from 0 to infinity of -1 to the n times 1 over n.
Yeah.
Or just this.
No, that's it.
That's it.
That's it.
That this is either for any fixed n, it's okay for n equals 5, right? To like a limit of 5 instead of a limit of infinity. It's going to be okay. So 1 minus 1 plus 1 minus 1 plus 1 minus 1, right?
Well, it starts off with a negative. But, yeah.
But if it was to the power 0, it would be 1. -1 to the power 0.
Oh.
Would be 1, right? So, yeah, this is either, I mean, it depends on where you stop. If you stop here, it's 1. If you stop here, it's 0. If you stop here, it's 1. If you stop here, it's 0. 1, 0. So, hand-wavy mathematician would say...
We went binary. We went
call it a half.
Engineering to mathematics to programming language.
Yeah.
Beautiful.
But anyway, so that was used somehow to show this result. But you can also show this result by fully proper math.
Wait, did they just say 0 plus 1 divided by the amount, which is 2, is a half? How did they get a half though?
Well, because you're bouncing between 0 and 1. It's always always 0 and 1, so just call it a half.
This is like half.
Yeah.
That's
Like, it's
funny.
not a very good way of doing it, but it works enough to prove this result. So
yeah, that's how it works.
Anyways, not directly related to our things here, but interesting nonetheless. I think. I think it's interesting that, like, we know very easily how to show that this converges, but to show that it converges to pi squared over 6 is a whole other thing, right? That's a whole other situation that's happening, right? That's a whole.
There's a hidden circle there.
There is a hidden circle there. Yeah.
There's always a hidden circle. That's what.
Somewhere, right?
Yeah.
Well, 3 blue, 1 brown? No, 3 brown, 1 blue.
No, 3 blue, 1 brown. 3 blue, 1 brown.
3 blue, 1 brown.
Yeah.
He always says that. It's always a hidden circle.
Wait, are you sure? Oh, yeah, you're right.
Yes.
Yeah, wherever there's pi, there's a hidden circle.
Well, yeah, for sure.
Then,
Alright,
well, that negative
any
one.
other questions that we were planning to do?
Yeah, I have one more. I
95.
got one more that I was planning on doing, which is 95 here.
Alright.
So let's try 95. Let's see if I get this again off by a negative. We'll see. So find the question actually is asking. Where is it? In the following exercises, given the geometric series, use term-by-term differentiation or integration to find power series for each function centered at the given point. Okay, so we want to find a power series for ln x centered at x equals 1. So how did I do this? Hold on, now I'm going to look at my results here. For this was 95. Yeah, we're good. We're good, yeah. So you'll see why we're good in a second. So f of x equals ln x. F prime of x is 1 over x. Right? 1 over x. Okay. The hint we have is that x is 1 minus 1 minus x. So we can write this as 1 over 1 minus 1 minus x, which we can then write as the sum n goes from 0 to infinity of 1 minus x to the n. Luckily, this is already centered at 1. It's already a series centered at 1. So f prime of x is the infinite sum n equals 0 to infinity of 1 minus x to the n. Now we want f of x, so we integrate both sides. Right? Integrate both sides with respect to x. Dx.
Wait. Why are we taking 1 minus x as the series? That's not a centered. Shouldn't it be x minus a? Which would be x minus 1.
You're right,
So
but
when you take out a negative, you get 1 plus x minus 1.
1.
Because you would take out a negative, that would 1 minus x times a negative 1 would give you
X minus 1.
minus
Minus
1,
1.
which is centered at 1.
This is already centered at 1, though. That's the thing. This is technically already centered at 1, because if I plug in... No, maybe
X minus a is the way you center things.
I guess it's just because when I'm thinking about centering, I'm thinking about what value makes this 0. Well, 1 still makes it 0. That's the important thing, is that the thing you're centered at makes this term here 0.
But
So
when you integrate this, you get a negative.
you would get a negative when you integrate it, because the derivative of that is negative, yeah.
Sorry.
We can keep doing it this way. I'm pretty sure you're supposed to turn that into x minus 1, but this way works as
The
well.
reason I'm hesitant to do that is because then we're going to have a negative 1 to the n.
Yeah, I was just thinking that.
We're going to have a negative 1 to the n out front here, which we could have. But that does add some part to it.
Is that change? Like, I don't know what the... It's just asking us to evaluate this, right?
Well, find f of x as a power series.
If it has to be
Is that-
centered at x equals 1, then I'm pretty sure it has to be the other way around. But
Is that the
maybe
difference
that's
that
wrong, I don't
of
know.
negative 1 that you were talking about, maybe?
It is possible, but it's not just negative 1. It's negative 1 to the n, which would be not the same thing. What question are we doing? 95? 95, yeah. What was my answer? Let me just see. What was my answer here? Oh, yeah. No, that is right. Yep, that is right. That was what I got wrong before. Okay, don't fully understand exactly why that is, but that is what it is. So 1 minus x to the n. This is not yet centered at 1. This is centered at 1. Negative 1 to the n, x minus 1 to the n. That is now centered at 1.
Yeah, I'm pretty sure it's always x minus.
I guess because my idea of centered means what makes the thing that's to the power of n 0. That's what my idea of centered was. And so by that definition, these are both centered at 1.
It does change all the other values as well, though, because if you do use this equation,
That's true, yeah.
it changes.
In the negatives in front of it,
Like,
or
'cause
something
now,
else.
okay, let's say x is 1. Well, now that's 0. But they're both, sorry, not if x, if x is 2, one of these becomes negative 1, and one of these becomes
Yeah.
1.
No, it does change. It does change everything. They're not
one of
they're not
these-
equivalent.
One of these become negative 1, and one of them become 1.
If I just say x is 2, then it would be 1 minus 2, which is negative 1. And here this would be 2 minus 1, which is 1. Right? So
Yeah,
it
but
would
then
it would change
it's
the
still. Would it though? Because now you'd have a negative 1 to the n on this side, and you'd also have negative 1 to the n times n on this side.
Well,
Like, it hasn't changed.
you'd have negative 1 to the 2n over here, because it would be negative 1 to the n, negative 1 to the n. And choose
Wait,
3 as x, choose x equals 5 as an example. It'll just like, so it'd be 1 minus 5 is negative 1 to the n, or that's not true. Negative 4 to the n, right?
Uh-huh.
And then here we'd have negative 1 to the n, 4 to the n, right?
Yeah.
Oh, but then this would
how
be
was
negative
it?
4 to the n, negative 1 to the n.
Yeah. So how has it changed?
Oh, yeah. Hold on. But this would be 4 to the n, negative... Yeah, that would be the same. Hold on. If I go back to 2, this would be negative 1 to the n.
And then this would be negative 1 to the n times 1 to the n.
Oh, and 1 to the n is 1. Yes.
Yeah.
So they would be equivalent.
This just makes it look prettier. So we're gonna keep it.
Would it though? You get negative 1 to the n times negative 1 to the n. Oh, I guess that'd be negative 1 to the 2n.
No, that's what I was thinking too. But careful, this would be 1 to the n here. This would be negative 1 to the n. This would be 1 to the n. 1 to the n is 1.
Yeah. Because I saw that and I was like, that's probably where it is.
Maybe they just want it in this form.
Yeah, then maybe what I did wasn't wrong. Is just missing. It's a little bit changed from the answer, so it's actually more than just off by the negative.
It's half off.
Yeah, but yeah, it looks like these are equivalent for any fixed value. Oh well, that also, I mean, it makes sense that they're equivalent because I'm saying they're equal, right? Like I'm saying I'm saying they're equal. So they definitely should be equivalent.
Maybe it has to do with if you just think of a number line.
Yeah.
If you're centering a number line, the proper way to center a number line on a specific value is having x minus your centering value or plus or whatever.
Yeah, it is. It is the proper way. I understand.
I don't. But again, it doesn't because it doesn't make a difference. They're equal.
Yeah.
All right. Yeah.
Okay. Well, anyways, let's. What should I do then? They're equal, so it doesn't matter. Why would it matter? Okay, let's do it with this one to see if I get the textbook answer with this bottom one. And if we don't, then there's something else wrong. So this would be negative 1 to the n, x minus 1 to the n. Then this is going to be f of x equals that sum converges, so I can put the series to the side here, times the integral, not times though, but of the integral. Negative 1 to the n can come out here, and this is x minus 1 to the n dx. So it's going to be 1. It's going to be 1 u sub. So it's going to be, I mean, the derivative of this is 1, so I can kind of do it in one step. So this is f of x.
I just have it still, yeah.
Times the sum n equals 0, n minus 1 to the n, and this is just going to be x minus 1 to the n plus 1 over n plus 1. Which is the answer. Which is the answer in the textbook. So, yeah.
So, if you maybe check yours again and see if you accidentally missed the negative sign then.
No, the reason mine is different is because...
Maybe it has something to do with the wavy proof of the 1 over n and the negative half, or sometimes 0, sometimes 1.
Yes, I think it might have to do with that, yeah.
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 Could be. Like, honestly, that's why I said it's half off, you know?
You know what?
Somewhere deep down the line.
The reason my thing didn't work is because when I integrated, I had to do a u sub. The derivative of this was negative 1. The derivative of this is negative 1. So that added an extra...
This was 1.
Yeah, but
this was negative 1.
This one's negative 1. This one's negative 1, right?
Yeah.
And this one's 1. So that's why I had an extra negative sign. And also, this was 1 minus x here, not x minus 1. Oh, but... No, I couldn't.
It would still...
Oh, no. Hold on. Does that... Can I say that's equivalent? Because that would be negative 1 to the n. No, but then I'm still missing this negative 1 to the n. Anyways, it doesn't matter what I did. This is the answer. This is
the answer.
Yeah, this is the answer. We got it now.
Wait, so you are supposed to center it on, like, with
it gives us their values.
Yeah, I guess you're supposed to do it like this. It's supposed to be in the form x minus a.
How is that different?
It isn't. It's equal. It's equal.
I don't get it.
I think my answer, as long as I didn't make any other mistake while integrating or anything like that, my answer should be equivalent. It's just that it's slightly written differently.
If math can't agree on itself, how are we supposed to agree?
No, it's just that we can't see their agreement. Ignorance is bliss, guys. This is not our forte, right?
Yeah, okay.
Leave that to the other guys.
My major.
No. M for the stem, but that's not the E's. No. All right, that's good. Are we done now?
Yeah, I guess so. 93, 95 we did 69 as well. I have 85 here, although I think we did 85, didn't we? 85 is... Oh, no, we didn't do 85, but 85 was also not important. Never mind. It wasn't important. So we did all the questions I wrote down. We did a bunch of Horowitz questions. Oh, yeah, there was that one extra Cauchy product question, but do you want to see me do it, or? are we okay with
Nah,
Cauchy Product?
I feel like you see, like, cause like I feel like we've done so many different things right now. It's like we
Yeah.
follow it right now, but like we're gonna seriously start to taper off if we do some like very
Yeah.
like
This
follow
was a lot of
it's-
studying, so we're
yeah,
we're
it's
good
like
for now.
because like the interval of convergence with the 4 different forms and the power series setting the form and
Yeah.
the re-indexing. Yeah, I feel like we're good. Unless
Okay.
someone else wants something.
Yeah, someone let me know if you want to see the thing. If not, I'm okay. I don't particularly want to, but yeah, I mean, I can.
I feel like I've spent most of this week in one of these tutoring things in one form or another.
Yeah.
Kind of weird. I feel like I spend more time in this than I have in lecture.
Yeah.
Right. So Adam should have your tuition fee then.
Yeah.
basically.
I'll gladly take that. I'll gladly take that.
Yeah. Yeah.
Adam, you should just go up to Horowitz and be like, you know what? I don't think we need you to run this class anymore. Do you mind if I be coordinator? I can coordinate
Yeah.
this class.
I'll be a
Yeah,
Couch
you-
teacher. Yeah.
Yeah. I mean, you know, I don't know if it's